Hello, this is Mrs. Nearing, and this video is going to walk through some general tips on acid-base practice number 1, which is some problems involving finding pH. Up here you'll see I copied and pasted the relevant equations. These are found on your equation sheet. These are things you do not need to memorize, but you need to know what they mean and when it's a useful time to apply them. So we're going to go through the problems on here that I circled. So first we're going to do a quick thing, talk about this Arrhenius definition of acids and bases, and this is the least broad definition of acids and bases, but maybe the most clear one. And by the Arrhenius definition, acids add H plus to a solution, and bases add OH minus. So these 5 substances that we gave you here, these dissociate when you put them in water. They dissociate into ions. So sodium hydroxide is a soluble ionic compound. It dissociates into its ions, so sodium ions and hydroxide ions. And then when it dissociates, you want to ask yourself, did it make H plus or did it make OH minus? In this case, it made OH minus. That means that it is a base. We said bases add OH minus. HNO3, this is a molecular substance, but it behaves like an ionic compound. So for right now, just assume that these 5 things we gave you just totally dissociate into ions. And when this dissociates into ions, notice that it makes H+, therefore it is an acid. This is actually part of one of these 7 strong acids, and these are all molecular substances that behave like ionic compounds. And how do they do that? What do we mean by behaving like ionic compounds? Is they totally dissociate. So we basically assume like 100% dissociate when you put them in water. Alright, so notice we're using like a one-way arrow here instead of a two-way arrow because they're basically go to completion. So let's scroll down and look at problem number 2. These are things called weak acids, and these are things that fit under we talked about weak acids and weak bases with the Bronsted-Lowry definition. We may not have called them weak acids or bases yet, but that's kind of usually what we're talking about. So let's look at what's happening here. And we're thinking about acids as being hydrogen givers and bases as being hydrogen takers. So this is an acid. It is going to give a hydrogen to water, and it is an equilibrium. That leaves behind F minus. Let's include states of matter here. And then the H2O becomes H3O, and it gains a positive charge. So that's our reaction there. And we can write a K expression for these. It's products over reactants. And we leave out water because it's a liquid. Liquids and solids always get left out of our K expression. You might also notice that sometimes people, instead of writing H3O+, they write H+. You can see right here how that happens. And this is the H3O+. It is, first of all, it is called the hydronium ion. And this is a little bit more accurate way of showing what's really happening in water, because what happens is when you have these H+ ions in water, they're these positive things, and they don't tend to actually hang out by themselves. They tend to go along and stick to the electronegative oxygen on the water. So the H3O+ is a more accurate way of showing what's actually happening in the solution, but then H+ is kind of easier to write. So a lot of times you'll see us write H+ instead of H3O+, but you can think of them as basically being interchangeable. So if someone tells you that the H3O+ concentration is 1 molar, that means the H+ concentration is 1 molar. All right, let's scroll down and look at some equations here, some calculations. So problem type 1, we're looking at the H-OH relationship, which is given right here. So basically we're saying that we know that the H+ concentration is 1.75 times 10 to the negative 8th. Our hydroxide ion concentration is the unknown, but we know that when you multiply these together, it is a constant. This constant is called Kw. So we can just rearrange this and solve for hydroxide. So we should find our hydroxide ion concentration is 5.7 times 10 to the negative 7th. All right, so problem number 4 is using this other equation. We're given the H+, and we're trying to find the pH. So we want to use this equation. pH is the negative log of the H+ concentration. You will need your calculator for this one, I would imagine, unless you are amazing at doing logs in your head. So when you plug this in your calculator, you should get 4.49. And then we can use this other equation, pH plus POH equals 14, to solve for POH. So POH is 14 minus pH, so 14 minus 4.49. So that would give you 9.51. And then we can use one other equation. So we're using three equations here, is this one right here. So the POH is the negative log of the hydroxide ion concentration. So to solve for hydroxide ion concentration, I want to isolate hydroxide. So I'm going to divide both sides by -1, and end up with this. And then the inverse of a log is doing 10 to the power of that thing. So 10 to the log of hydroxide is just hydroxide. And then 10 to the, so basically we're saying the hydroxide ion concentration is 10 to the minus POH. So this equation is not on your equation sheet. You just need to be able to rearrange this equation, which is given. So if you go through and you solve that, you should end up getting 3 times 10 to the -10th in this case. And then let's scroll down to problem number 6. Again, similar to the one we just did here, where we're given a pH and trying to find H+ concentration. So we know that pH is the negative log of the H+. So to rearrange this, first I'm going to move the negative over here, okay, and then I'm going to go 10 to the on both sides. So you end up with H+ equals 10 to the minus pH. So this is an equation that, again, is not on your equation sheet, but it's just a rearrangement of an equation that is on your equation sheet. Okay, and here's another example of this. So you're trying to find, again, we know that pH equals the negative log of the H+ concentration. So to solve for H+, you're going to go 10 to the minus pH, which is 10 to the minus 2.55 in your calculator. So that's basically, I think we kind of went over all these different equations that you might need to use here. Okay, so these are your basically 4 equations you'd use in any sort of calculation. And then scrolling down to this last page, we're just looking at strong acids and strong bases. So the key thing to recognize here is if you have a solution of something called a strong acid, which, how do you know it's a strong acid? Well, for right now I'm just telling you these are strong acids. If you've got a solution of strong acid, then it is going to completely dissociate into these ions. That means, like in this case, if you have 0.5 molar HCl, you're going to end up with 0.5 molar H+ and 0.5 molar Cl-. Now the Cl- we don't care about, it's just going to be a spectator ion. Remember our chlorides and our nitrates and those guys. So this isn't doing anything. What's affecting the pH is this right here. So if we say we have 0.5 molar HCl, what's important is that we have 0.5 molar H+ ions. And then we can use our those mathematical equations we were just doing, that pH is the negative log of the H+ and solve for pH here. Same thing's happening in problem 13. The only difference here is you have to calculate the molarity first, because you're not given a molarity, you're given a grams and a volume. So you got to make sure you convert your grams to moles and convert your milliliters to liters. Okay, and same thing down here with your bases. Your concentration of your base is the same as the hydroxide concentration. All right, and it looks like my time is up.